First of all, today we'll talk a little bit about asymptotes. Remember, when we're drawing them, curves always bend towards the asymptotes. Okay? They will never cut a vertical one because that's an exclusion in the domain. The horizontal and oblique ones are telling us what happens out at the extremities. So they are allowed to cut them if they need to. If we can rewrite a function that is a rational function, what we call a rational function, so you have a polynomial on the other, you could rewrite it as the quotient plus the remainder over the divisor. Ax, the denominator, the divisor, you solve that, that'll find your vertical asymptotes because the bottom of the fraction can't equal 0. The quotient will tell you the horizontal or oblique asymptote, and the top of the fraction, that will tell you whether it cuts the horizontal or oblique asymptote. Solve that one equals 0, and it will tell you where if it does. So let's just do a quick one there. Already been factorised for us to make life a little bit easier there. If I did a polynomial division, I would have to expand it out, of course. X squared minus 1 into x squared plus x minus 6 goes once. Take away, we have a remainder of x minus 5. We could rewrite this fraction then as 1 plus x minus 5 over x minus 1, x plus 1. Now let's get all our information. X-intercepts, I'll go back to the first one because the top's nicely factorised for me. So I can say I've got x-intercepts at -3 and 2, plot those in. Y-intercept, I'll sub 0 in, that's always an easy one to find, we get 6. Vertical asymptotes, bottom of the fraction, plus or minus 1. Let's dot those in. And we have a horizontal asymptote at y equals 1. Let's put that one in. Does it cut the horizontal asymptote? Well, yes, it does. X minus 5 would equal 0, so I know it cuts it at 5, at x equals 5. That's enough information to draw our graphs using the idea that we know it's going to bend towards the asymptote. Therefore, as we're working from left to right, we must get some sort of hyperbolic type shape. It's going to bend towards those but pass through -3. In between the two asymptotes, it must be a U sort of shape like that, because if it went down, it would have to cut the horizontal asymptote, and we know it doesn't cut that one other than at x equals 5. So let's go up. Now this next one becomes interesting. I've got to go through 2, I've got to go through 5, I've got to bend towards the asymptotes. Whoa, very dodgy. But it must do something like that. It starts down here at -infinity, comes up through 2, goes through 5, it would go up, but it must then come back down and inflect, so it will go asymptotic to our line there. Alright, let's try this one. Again, let's do a polynomial division. X squared into x cubed goes x. We get a remainder there. Well, we can keep going. X squared into minus x squared goes -1. Remainder of 4x minus 4. Okay, this is how we could rewrite that fraction. Let's get our information. X-intercepts, -1, 1 and 2. Y-intercepts, substitute in 0, we get -1/3. Vertical asymptotes, -2 and 3. We have an oblique asymptote in this case. Y equals x minus 1. Draw that in. Seems a silly question to ask when you look at what we've drawn, but can it cut the asymptote? Well, clearly the answer is yes, because it's going through 1. But if we were unsure, let's look at the top of the fraction. Oh, sure enough, that would give us x equals 1. Let's draw it in. The first bit must be trapped in this little triangle here, because if it was to go in the other section, it would have to cut the x-axis, and we don't have any other x-intercepts, so we know it doesn't do that. Now, the next section, there we go. Must start up the top here. I know it can't start down the bottom because it would have to cut the oblique asymptote, which it doesn't other than at x equals 1. So it must start up here, comes down to -1. At some point it needs to get through the y-intercept and go through the x-intercept. But now it's got to go asymptotic to the vertical one, so it must turn, come back down through 2 and go asymptotic again. Which just leaves us to the right-hand side of that asymptote, and it must be trapped in that little triangle there. And there's a sketch of our graph. Whilst we're speaking about asymptotes, reciprocal functions, they tend to have asymptotes as well, depending on what we're drawing. How can we do it? Well, if we know what function x is, and basically we're saying we're just going to turn this curve upside down. There's key things to look for. What do we know? We know the bottom of a fraction can't equal 0. So therefore, my original curve, wherever it equals 0, it will become undefined. Here's a random curve here that I've drawn and tried to get all sorts of different features in there. We've got some asymptotes and what have you. So if I was to turn this one upside down, I know I've got 3 vertical asymptotes, the x-intercepts become vertical asymptotes of my new curve. Okay. But the reverse will happen. If the original graph had a vertical asymptote, well, when I turn it upside down, it will now become an x-intercept. Sort of. Okay, let's go back to this graph. We have, on the original graph, a vertical asymptote there. So when I turn it upside down, I have an x-intercept. Sort of. You'll notice I've put a hollow circle there. The actual point is not included because you are saying I'm going to turn this curve upside down, but that x value wasn't in the domain of the curve I'm turning upside down. Therefore, it can't be in the domain of the new one. It's like a composite function. If it's not in the domain of the original one, I can't all of a sudden magically get it in the domain of the composite, what we've made it. You'll notice I've now dotted in there because, hey, turn 1 upside down, you know you're going to get 1. So anywhere where it was 1 on the original curve, it would still have a y value of 1. The same would be true for negative 1. You turn negative 1 upside down, you get negative 1. My horizontal asymptote, originally it was less than 1. Turn a number less than 1 upside down, you get a number bigger than 1. So I know on the new curve my horizontal asymptote will be above 1. I'm just estimating here, so I've just put it above there so I get some sort of a sketch. If the original graph is increasing, then the reciprocal will be decreasing, and vice versa. The sign's not going to change. Turn a positive upside down, you still get a positive number. So this one here then, I know the curve will go in these sections. Here's my logic. Let's work left to right. I have the curve is below 1 and positive. So the new curve will be above 1 and positive. But hang on, it doesn't go past the asymptote, so it won't go past the asymptote. I know I'm in that section there. The next bit, I have a curve that is totally above 1, so I'll get something that's totally below 1, and so on, and so on, and so on. So that's how I've worked out each of the individual sections. We haven't done the calculus on it yet, so you might just have to trust me on this one. But if you differentiate 1 over function x, you get minus the derivative on the function squared. What that basically means is stationary points, and stationary points are when the derivative is equal to 0, of the original curve will still be stationary points of the reciprocal curve. All we really need for that is, okay, I know the curve is going to turn at the same x values. The y value will change, of course, because we're turning the y value upside down. So I've moved my turning point to, well, I've made an estimate. It was originally above the asymptote, so now it's going to go below the asymptote. It's going to stay positive. Yeah, I've put it about there. There we go. Now we can draw it in. There's our reciprocal. We've turned that graph upside down. But notice the point discontinuity there at the x-intercept. 5C, we get to play.